have a copy of them. And I wasn't here last time. I wanted to be here last time because we're going to talk about Bitcoin and blockchain and stuff like that. But at the last minute, the meeting got moved to the same Tuesday as
the caucuses.
Primary caucuses. So I ended up being a good, dutiful citizen and went to that instead of the meeting. So who all here was here for the blockchain Bitcoin one? Okay.
So how many don't care about our democracy?
Well, certainly the guy who planned it.
So the topic that was listed was Byzantine fault tolerance, and I'm going to talk about Byzantine fault tolerance, right? But I wanted to talk a little bit about it in a broader perspective, and that's why I use the term distributed consensus and diffuse trust systems. So the question is, why do we care about distributed consensus? Distributed consensus enables diffuse trust systems, and it enables decentralized computing infrastructure. And when people first developed distributed consensus in the 90s, the concern wasn't about decentralized computing infrastructure. The concern was really to get rid of really obscure types of faults that you might have in your private server class, and less about some of these new things. But with blockchain, and a lot of the stuff that's happening with blockchain, having decentralized computing infrastructure becomes really important. And so there's been a renaissance recently following algorithms for that application. So if I have a diffuse trust system, I can have a secure infrastructure outside of the firewall because I distribute the attack surface. And so I can get comparable levels of security and invulnerability to attack because I've got a distributed, I've got an attack surface that doesn't have common failures. And what this means from a standpoint of building systems is that I can disintermediate current centralized computing infrastructure systems. So there are a lot of business models that people are proposing, a lot of startups whose goal is to disrupt the current, Google, Facebook, Amazon siloed systems. And so some of those would be computation in the fog versus computation in the cloud. Some people call it fog, some people call it neighborhood networks. So Space Monkey is an example of computation in the fog, where you're using edge devices and you're communicating directly with the local devices, not going back to the cloud and then back out again. Distributed AI. I think last week, didn't Will Bone talk last week?
We did talk last week about
last week or last time?
Or last time we talked. So what we talked about last week was we talked about Merkle trees, hash cache.
Okay.
We talked about sort of the future with distributed ledgers, a bunch of different applications.
He didn't talk about it.
Will didn't come.
Yeah, he didn't come. Okay, so Will Bone has a blockchain-based distributed AI framework.
Cool.
The idea is enable that. Smart contracts, should probably talk about that a little bit. Internet of Things, secure Internet of Things, not Wild West Internet of Things, etc. So I won't go into a lot of details about those, but that's the motivation. So what does diffuse trust look like? If you think about the centralized, I've got a castle and a moat, multiple walls, and my firewall and all of the secure policies that I use to keep people out of my servers. But it's a single source, it's a single target, it's a single place that they can attack. And if I can find an exploit that gets me through the moat, through the walls, through the gate, then I own that system. And so lots of the exploits of major computing infrastructure come because you have this very centralized system and there happens to be a common mode failure. Some SSL exploit or SSH exploit or SQL exploit, something like that allows you to escalate and get root privileges. Whereas in diffuse trust, the ability to exploit the system requires that you make multiple exploits against multiple systems. So it's a cellular distributed topology. By cellular, I do not mean cell phones. I mean cellular as in clandestine organizations, spy rings, resistance organizations, where only parts of it know the other parts, and if you break down into one cell, you don't get the whole organization. So defeating each node requires an independent exploit. So if I have a 1 in 1,000 chance of exploiting a server, and I have to exploit 5 servers to take down the whole system because I'm using the distributed diffuse trust system, then I've got a very low likelihood of being able to make the exploit. So no single points of failures, no commonwealth failures, and as long in these systems, as long as a majority or typically supermajority of the nodes are not exploited, then the system is trustworthy. And so obviously Bitcoin is an example of that type of a system. So you're thinking about cooperation between peers versus an authoritarian hierarchy. So there are several types of distributed consensus. The one that's most popular is proof of work, and that's Bitcoin. And it's a very elegant approach to distributed consensus. It solves a lot of problems in a very elegant way, except for one problem. It's highly inefficient, has very high latency, and very low throughput. So you get lots of good things with it, but you don't get high performance. Proof of stake, which I call asymmetric proof of work, because most proof of stake systems are really proof of work, but there's an asymmetry, which means that the one that wins the competition doesn't have to work as hard as everybody else. So it's sort of like you're taking turns. It's like a round robin, but under the hood, it's essentially proof of work. So that's somewhere in between. It's a little more complex. It's more efficient, lower latency, and higher throughput. Byzantine agreement, which has been around for quite some time, since the 90s really, is the most complex of the protocols, but it is also the most efficient, has the lowest latency and the highest throughput by as much as 2 orders of magnitude, where you might get 2 to 10 transactions per second on Bitcoin. You can get thousands or tens of thousands with a Byzantine agreement protocol. And proof of stake might be in the hundreds to low thousands. So it just gives you an idea of where the spectrum is. And then there are hybrid systems that use combinations of both, say, Byzantine agreement, proof of stake, or might use combinations of proof of work and proof of stake based on different applications and different features that people want to take care of. So another term for Byzantine agreement is permission distributed consensus. And the reason for that is and there's a really good paper that talks about this. So I've got the link up there for you. But Swanson wrote a paper that explains in detail the business case and the technical case for using permission distributed consensus or Byzantine agreement versus using proof of work like blockchain. And the main trade-off is that with Byzantine agreement, you don't have a built-in solution for the Sybil attack problem. How do I get hosts into my consensus pool, and how do I govern them and manage them? That is something that isn't built into the algorithm. That's something you have to bolt on. And so Bitcoin, fanboys, they love Bitcoin because it takes care of that problem. But if you're willing to manage the permissioning or censorship process, you can get a huge benefit in terms of performance by going to a permission distributed consensus. So, and sometimes people call that censorship, right? If I'm requiring some sort of permissioning process, that I'm censoring the host. I'm not allowing just anybody in the world anytime they want to join my consensus pool. For many applications is a good thing. So I get higher speed distributed consensus. Some applications. So Bitcoin is cryptocurrency. If I go beyond cryptocurrency and start thinking about what I use distributed consensus for, I can use it to manage databases. I can use it for open storage, like MadeSafe or Storage, Big Chain DB. There are various applications. I can scale it by using a combination of distributed consensus and distributed hash table. A lot of people use Cadenlia. I can have a secure peer-to-peer transaction system. So a lot of people use Byzantine agreement for settlement. Ripple, Stellar, C3, Hyperledger, smart contracts. There are other various groups besides Ethereum, which is a proof of work system that are building smart contracts. Identity, that's something I've worked with recently with Evernet. It's an identity system based on the blockchain. And reputation, which is also something I've worked with. So there are a lot of applications where you can manage infrastructure outside of the firewall, in the cloud, distributed across peer-to-peer hosts, multiple organizations where you have peer organizations, and not all members of the same corporation, and have a way that work together. So the core problem, the reason it's called a Byzantine agreement, is there is the Byzantine generals problem. And the basic idea is that I've got a general and some lieutenant generals, and he sends a command to attack. And if the majority of the generals attack, they win. If only one general attacks, or not a majority, they might lose. And if I've got Byzantine generals, that means they might lie. They might try to trick the other guys, right? So malicious information makes it a Byzantine problem. And there are some good proofs that say you can't converge with only 3 generals. So the analogy that is made toward the Byzantine era, the original paper for this is Leslie Lamport. So you can, I'm sorry that text is a lot smaller than I thought it would be. In a Byzantine agreement, a valid consensus is guaranteed despite some fraction of the participants acting in a malicious and erroneous manner. Now, a lot of, like we had one of the sessions on Raft. Raft is a way of coming to a consensus if you have nodes that are erroneous. They might fail, they might not be available, but not malicious nodes. Byzantine agreement allows you to have malicious nodes, nodes that are intentionally trying to confuse the consensus. They lie about their votes. They vote differently to different people. They, try to slow down other nodes. They try to do anything they can to cause the consensus to not form. And so it's a much more difficult problem to ensure consensus, despite the fact that you've got Byzantine faults. So malicious packets are typically the hardest thing. So any algorithm that is tolerant to Byzantine faults is called Byzantine fault tolerant. There are, of all the Byzantine fault tolerant algorithms, there are 2 features that they typically strive for. One is liveness, the other is safety. Liveness means that you come to a consensus in bounded time. So, for example, nodes not responding, just being quiet and not answering, not responding to messages would cause a problem. Safety, that means if you come to a consensus, that everybody comes to the same consensus, or the group comes to the same consensus. So the idea is that I want to have a state replication so that I can have a sequence of transactions, typically in a shared public ledger or a database, so that I can do state machine replication. So for many years, Byzantine fault tolerance was an academic exercise because it was really non-performant. It just was painful. Nobody took it seriously. And then in the late 90s, Castro et al. Came out with something called practical Byzantine fault tolerance. So we're going to go through the practical Byzantine fault tolerant algorithm, because that is sort of like the mother of all Byzantine fault tolerant algorithms. most of the research work that has been done since '99 departs from this one. They basically say we start with practical Byzantine fault tolerance, and then we'll tweak this, we'll add this, we'll make a change to that. So if you understand PBFT, you can usually understand everything else that anybody has done in the space. If you don't understand PBFT, then it's usually just confusing, because usually they assume you know PBFT really, really well before they even publish the paper. So I think this will be useful. So if I have a synchronous system, I have certain guarantees. Well, the problem is that if I don't control the host, I can't guarantee synchronicity. And so Byzantine faults are a result of the fact that I have hosts that I don't control, so I can't guarantee synchronicity. So I need some way to come to a consensus to cite the fact that I don't have a synchronous system. So I need some sort of asynchronous algorithm that works despite the fact that I don't have synchronicity. So there is a fundamental constraint, and that is I can't have a completely asynchronous system. And in fact, if I have an asynchronous system, it's impossible to come to consensus even if there's one faulty node. So that's there's a seminal paper on this by Fisher, Lynch, and Patterson in 1985. So the workaround is what is called weak asynchrony. So I want to have sequential consistency. I want to make it linearizable, and I want to be able to achieve state machine replication. Because if I have state machine replication, then I can do just about anything I want to do. I can, manage the database. I can, manage the ledger. Any kind of computing facility kind of works. So the goal is to be able to achieve state machine replication despite malicious faults. So we talked about some of the Byzantine faults. In a Byzantine system, we have honest or non-faulty nodes. We have dishonest or faulty nodes. The reason we use the term honest or dishonest is because the hardest thing to solve is the fact that they lie about the results, not that they fail or don't respond or go offline. Right? Those are easy problems to solve, relatively speaking. It's the lying about results that's hard to solve. So we want to get liveness. We talked about that. Weak synchrony comes from having timing bounds. So that means that we don't have to all be in sync, but we have timeouts. And as long as things happen within those timeouts, then we have liveness, we make progress, we make decisions. And so that means that it's a reasonable constraint. And the delay doesn't grow faster than time. In other words, it moves along, with some sort of timing bound. So you have like an interval, little h to big H, which is anything has to happen within those timing bounds. To get safety, we need to have a quorum of non-faulty nodes that come to the same joint decision. So quorum management is an important part of the algorithm. And so the quorum forms the consensus. And we need to form the consensus despite the fact that some of the nodes never respond within our timing bounds. Right? So we have to make some guarantees about enough of the nodes respond within our timing bounds that we can form a quorum and come to consensus. So some assumptions. All messages are signed. This allows us to determine who said what when. And for performance reasons, most of the early papers used message authentication codes for signing with shared secrets. The problem is that those have additional problems because if I have a shared secret, I don't have non-repudiation capability, so I have to add additional checks like digests of messages to make sure that we're talking about the same thing. And 20 years ago or even 10 years ago, the performance difference between a message authentication code and a true digital signature was significant. Now with high-performant ECC signatures like the libsodium, the performance difference between that and a message authentication code is much, much reduced. So, for example, RSA signatures for the same level of security can be from 100 to several thousand times slower than an ECC signature. So just updating the algorithm to use digital signatures means we can simplify some things. And in fact, I'll talk about the Plenum implementation that I worked on. It's an open source implementation. We used digital signatures instead of method authentication codes, so we were able to get rid of the digest and without a serious performance hit. And I just said all that. So in a PBFT, you'll see the letter F used all the time. And it doesn't mean bad stuff. It just means there are most F faults on any step in the algorithm. That's your limit. You make that assumption. You can't prove that. You just assume that. So you have to have some statistical proof or some other outside information that allows you to be confident that you never have more than F faults on any step. Honest nodes behave deterministically. That means an honest node, the code you can guarantee runs a certain way. You're not going to have random stuff happening in the honest nodes. You make that assumption. Honest nodes fail independently. If an honest nodes fail, they don't all fail the same way. You don't have a common mode failure. Weakly synchronous, bounded time to respond. All right, so those are the basic assumptions. Let's look at the core. This is the core information in the algorithm. When you read through the papers, they make some invariants about proving that it doesn't work. And if you understand this, then you can understand most any BFT algorithm. So N is the total number of nodes. It's the size of your consensus pool. Correct agreement is guaranteed anytime I have F+1 nodes. And the reason for that is that I only have at most F dishonest nodes, which means anytime I have a group of F+1 nodes that are in agreement, that means that at least one of them is honest, which means if they're in agreement, it must be a correct agreement, because the honest one will never agree incorrectly. By definition, they're honest. Now, F+1 nodes may never ever agree, right? The dishonest ones don't have to agree with the honest one. But if I do have F+1 nodes that are in agreement, I know it's a correct agreement. And so that understanding is what bootstraps all of the other proofs in the algorithm. Now, given that I could have F nodes that don't respond or bad, how do I guarantee that there is agreement? Well, I need to have a majority of honest nodes. If I have a majority of honest nodes, then I know that at least F+1 nodes will be in agreement, because F of them could be dishonest and therefore not agree. So if I have two F+1, then there's at least F+1 that are going to be in agreement. So so I need to have a majority. Now the problem is that even though I might have two F+1 nodes in agreement, it may be that some of the honest nodes are delayed. They don't respond within my time bounds. So I don't just have the problem of F nodes that are dishonest. I also have F nodes that might be honest but don't respond within my time bounds. So in order to guarantee that I have a live agreement, I need to have an additional F nodes so that I have enough honest nodes that at least two F+1 will respond, despite the fact of F honest nodes not responding at all. And in the two F+1 nodes that do respond, F might be dishonest. So they might be lying, but they're still responding. So that's where you go from F+1 to 3F+1. And so PBFT, 3F+1 is the number that says, hey, we need this many nodes. And so in some of the papers, they sort of hand wave the proofs, especially in the original one. They kind of hand wave this next one. So I not only need a live agreement, but I need a safe agreement. And this is the one that's a little more complicated. So I have 2F+1, which is my minimum quorum size. N minus F is the quorum size that ensures a quorum is formed in bounded time. And think about it, I have N nodes. F may not respond in bounded time. So the largest quorum that I can form is N minus F. So if I can get N minus F, if my quorum size is n minus f, then I know that I can form a quorum. Because at worst case, f may not respond. They don't have to be in agreement, but at least they're responding. So if I take that constraint plus the minimum quorum size is 2f plus 1, then I need to achieve this other invariant. And this is the one that they tend to hand wave. And I had to look to find a really good proof for this. It's not in the papers. They just sort of hand wave it and say, this is, when we achieve this invariant, take our word for it. That is, the intersection of any quorum partition will include at least one honest node. And so that's called partition safety. That means that any two quorums that might form will always be in agreement. You can't have two quorums that come to an agreement that's different. They will always, any two quorums that form, no matter what, will always be in agreement. And with that, then you know that you're always going to get the right answer. So this is vital to the thing, because a lot of attempts to come up with Byzantine fault tolerant, this is where they fail because they couldn't get this property. So we have these two constraints, and so the problem is, given these constraints of the quorum size, find the minimum n that ensures that an intersection will have at least one honest node. And that proof is in terms of the cardinality of the sets. So cardinality, if I have a set, the cardinality of the set are the number of elements in a set, and that's represented by S in vertical brackets. So let's look at a partition. So we have partition Qi, which is a quorum. Partition Qj is another quorum. This is an overlapping partition. So there's an intersection between Qi and Qj. And then the union is the whole space, right? So I have this property that the intersection of Qi and Qj is greater than or equal to f plus 1. What does that guarantee me?
That there's at least one honest node.
That there's at least one honest node. That's right. So I need that there is at least one honest node in the intersection. And they share that one honest node, which means that honest node can't have a different answer for both quorums. He's only going to have one answer. And since he's in both quorums, it's going to be the same, which forces both quorums to be in agreement. If both quorums intersect with at least one honest node, they will be in agreement, because an honest node can't lie. And so we can't tell one quorum, I vote this way, and the other quorum, I vote a different way, which is the fundamental problem. So as long as we have that property, then we can guarantee live safe agreement. So the proof, which most people don't provide, they just state this, is that if I look at the property of overlapping partitions, the cardinality says that any two partition quorums that are form a partition, the sum of their cardinalities is the cardinality of the union plus the cardinality of the intersection, because the intersection is counted twice. All right. So if I rearrange that, I get the second phrase here, and now I can apply this constraint of the f plus 1. So now I just have to solve based on the cardinalities for this constraint of s plus 1, and that gives me that n equals 3f plus 1. So that proof is not in the papers.
Sam, I have a question.
Yes.
So just a bit ago, you said because the sets overlap, that's if we've proven that there's an honest node in the intersection.
Yeah.
Then we've proven that both quorums in both have to be.
They're not an honest node, the same honest node. Yes.
But so explain to me why the honest node can't be outvoted by a majority of nodes in the other quorums.
Well,
What is it about that makes it so that it can't vote?
Well, because the other property is that a quorum has to have a majority of honest nodes. So a majority of honest nodes have to be in agreement within each quorum. So I now have two quorums that come to consensus because they have a majority of honest nodes. And now I want to prove that both quorums come to the same consensus. And since they share at least one honest node, that honest node cannot come to a different consensus for two different quorums. And also be honest, that's right. So that's the core proof. So do you want me to go through this you want me to go back through this? You want to, the math's pretty, I didn't leave out any steps, so you should be able to follow, yeah.
So in the case of the cardinality of estimates, is this like the number of output states that may be?
No, it's the number of members in a
Okay, so it is just the number. Of
just the
members.
number of
Is
members.
it variant in the number of output states as far as, if I have a huge, like possible, like instead of just a true or false, like I have a, a high cardinality value that we may be agreeing upon. Is it variant to that, or do we have to tweak things based on?
Yeah, the algorithm basically is going through a sequence where you have to agree to a sequence numbering, so you agree to the ordering of operations, and each stage you come to a consensus.
Okay. So
Right.
so okay, that makes sense. That's good.
So this is what the algorithm looks like. It involves a three-phase commit. And from the client's perspective, the client broadcasts or multicasts a request to the replicas. So replicas is the term they use for the nodes in your consensus pool. So the minimum number that you need, if F is 1, is 3F plus 1 means 4. So in lots of the examples, they just give you 4 nodes because that's the minimum number you need to have this agreement, because you need 3F plus 1. Right?
In the limit, there's 2/3 of your network needs to be trustworthy. Right?
Well, no,
In the limit,
no, 3/4.
3/4.
You have 4, so you need 3 honest nodes. At most, you can have 1 dishonest node.
So if it's 3F, you can deal with F failures, right?
That's right.
And you need 3F total nodes.
No, 3F plus 1 total.
Right. 3F plus 1 total nodes. So in the limit, for really large values of N and F, it's roughly 2/3 of your network has to be trustworthy.
As F goes to as F goes to infinity. You're right. Yeah. So it's a super majority.
Yeah, right.
And some other Byzantine agreement protocols make trade-offs where the requirement is 5F plus 1. And so there's a protocol that has a 2-phase commit, but you have to have 5F plus 1 nodes to come to consensus. And so you get speed at the cost of many more nodes, right? So the clients broadcast requests because they don't know which one's the primary. So they just broadcast requests to all the nodes in the pool. And then the pool does a 3-phase commit. The client doesn't see this going on, right? The client just broadcasts a request. Sometime later, it starts to get replies back. When the client gets F plus 1 matching replies, he's good. Because the only way I can get F plus 1 matching replies is at least one is honest. That means if they all match, then it's a correct reply, and I can trust it. So the client doesn't need to have see 3F plus 1 of anything. It just needs to see F plus 1. It's not guaranteed that it will see F plus 1 unless they come to a consensus. And so one of the things the client can do is have a timeout that if he doesn't get F plus 1 replies after a certain amount of time, he starts over and says, hey, rebroadcast. That will trigger a view change, which we'll get to. So the client deals with 2 messages, a request message and a reply message. And so the O is the operation. So if I want to write to a database, O is my, write to the database or read from the database or make some change, right? State change. T is the request timestamp. So I don't have real-time clocks, I have logical clocks, and I have a timestamp which really just orders my request. The client says every time I do a request, I'm going to give it a number, and that's my timestamp. So I know when I get replies that the replies correspond to this request. Client has an ID, and sigma C means the client signature. So everything's signed. And in most of the algorithms, like I said before, they use either media authentication codes, digital signatures, or some combination. But for things that are outside of somebody's firewall, you really want to use digital signatures because there's just too many ways that you can mess up message authentication codes outside of somebody's firewall. The reply has a view number. Okay, so the view number we'll see is a way of ordering. And for those who are familiar with RAF, the view number corresponds to who is the primary at the current point in time. There's a replica ID, so each replica, which is the term for any of the hosts that are in the consensus pool, R is the result of the operation O. So if there's a return from the result, then client gets it back, and each replica signs their reply. So the client knows that it came from a replica, and it knows that it wasn't a duplicate, right? Because a malicious replica might send multiple replies and pretend that he's somebody else. So if I have digital signatures with non-repudiation, I know who sent the signature, and a dishonest node can't pretend to be somebody else because the signature won't validate. So once the primary replica, and the primary replica is deterministic. So it's just v mod n. So whatever the view number currently is, that determines my primary replica. So you can see already there's a problem brewing here, because if I have F dishonest nodes, as I'm cycling through my views, every time I hit a dishonest node, that view is going to be gone, and I'm going to guarantee I'm going to hit those every time. I don't skip them. I don't skip the bad primaries, so I'm going to have to deal with them every time. And so some of the other BFT protocols add extra complexity so that you could prune dishonest nodes and stuff like that, right? But PBFT is simple enough that it says, well, we're not going to worry about that right now. So the pre-prepare message is basically so that every node can be notified that a client request has occurred. And the primary is the one ordering the requests. So he gets to determine what order things get entered into the log. And so he broadcasts this because he's the primary, he gets to determine the order. And so the pre-prepare message has a view number, which corresponds to the primary. They're deterministic. He picks an N. So that's the sequence number of events. So the primary gets to pick the N. There is a digest of the message. M is the original client message. So instead of sending the whole message, you can send a short digest just so that people can validate that we're talking about the same message. And if I have digital signatures, I just have to send an index, because the honest nodes are non-reputable and they won't lie about the index, so I don't need a digest. And then the primary signs it, so everybody knows it came from the primary. So every message is signed. So now that everybody has a pre-prepare, this is the main phase. The main phase is now we have to have a quorum of nodes decide to vote to accept the message that was sent by the primary. And so each node sends a prepare message to every other node. So if I have 4 nodes, I'm going to have, 3 messages sent by each of the 4 nodes to everybody else. The primary doesn't necessarily have to send a prepare, because the prepare message includes the same information the pre-prepare includes. So basically, this allows every node to know what every other node is voting, how they're voting. So every node gets to know the vote of every other node. And so the prepare is the same as the pre-prepare, except that now it's signed by each replica instead of by the primary replica. So a replica will accept a prepare from another node if the signatures match and the DND match the pre-prepare. So right then it goes, well, if somebody's lying about the prepare, lying about their vote, and it doesn't match, I can throw it out. And I will be prepared if I get a pre-prepare and 2F matching prepares. So why a pre-prepare plus 2F matching prepares? That's 2F plus 1 votes. That guarantees that I have a quorum with a majority of honest nodes voting to accept the pre-prepared. Yeah, their own vote, that's right. Including their own vote. So now I know that I have a quorum and we agree on N and M, which is the client message, N is the order for the given view B. So we now have ordered the messages. We now can write it to the log because we have a majority vote. And this is where the invariant of multiple quorums comes in, because if I have a quorum and I have the 3F plus 1, then I know that I couldn't have possibly gotten a quorum of preparers, and there'd be another quorum out there that doesn't agree with mine. So everybody knows that whatever quorum they're a member of, and the quorums don't have to have the same set, right? They just have to intersect one honest node. So I could have two quorums that are formed because they're partitioned. So this node might be able to talk to some of the nodes, this node talk to some other nodes, and between the two of them, there's two quorums that are formed. But as long as they overlap one honest node, they will agree to the same thing. So it doesn't matter that there's two quorums, they're both in agreement. So they both can proceed to the next step, which is to commit the operation. So once they have received a quorum of preparers, then they commit. And they need the commit phase because once a node is prepared, it may not respond, it may have a problem at that stage. So we have to have one additional stage to guarantee that everybody commits and writes and performs the operation. So now they perform the operation. So each backup performs the operation, if it has, and then they send the commit messages. Once they perform the operation, they send the commit messages to all the other nodes. So now we're ensured that the operation was performed by a majority quorum, right? So the preparer just says, okay, we've agreed that we want to perform the operation. The commit says, we performed it and a majority performed it, and that majority was an honest majority. Therefore, we know that we did it right. And therefore, we can now respond to the client. And
There's a potential rollback if that commit phase doesn't work out.
That's right.
So there can't be any permanent change that happens for the operation. Or
that's right.
Or the operation has to be guaranteed to go through after the commit phase.
That's right.
With no errors.
Right. So that's what the view change does. And this is the problem. So now if any node has received 2F plus 1, include their own commits, it knows then that it can tell the client, hey, 2F plus 1 of us have performed this operation, written it to the log, you know it's done. And it sends it back to the client. Now, if F plus 1 don't respond to the client says, hey, it didn't happen. As far as I can tell, it didn't happen. So it's in the log, but it didn't happen. But if F plus 1 responds and the client's good, he's done. He can send his next request. And all these requests don't have to happen sequentially. You can queue them up because you can have multiple views going on at the same time, as long as everything's ordered. Yes.
So what if one node got F plus 1 commits from the other nodes, but for some reason the other nodes didn't get, none of the other nodes
Well,
got
no,
F
this
plus
is the
1.
client. The F plus 1 is the client.
Okay.
So if he gets F plus 1, there's only one client.
Okay.
I mean, you can have multiple clients, but for any given client, he's the only one. He determines.
So it either it knows or not.
It knows or not.
Okay.
And so the reply, which we're going to talk about, is basically, hey, the operation performed. Here's the result of the operation. F plus 1 did it. You're good to go. The client can walk away and be happy. So one of the problems is that we have an infinite log. So what we want to do is we want to truncate the log. We want to have checkpoints. So we have the same problem. How do we agree on when a checkpoint occurs? So what happens is that we have an algorithm for checkpoints. We decide, hey, once an hour we want a checkpoint, or once a day, or after so many entries we want to form a checkpoint. And so whenever that condition occurs, all of the replicas send out a checkpoint message. The checkpoint message has a digest of the log state. So whatever their log state is at the time that they want to do the checkpoint, they send this out. And they use a digest because the log state could be a big thing, right? It's all the entries in the log. You want to have some digest. So a Merkle tree is a way of digesting your log, right? That's why they use Merkle trees for Bitcoin. It's a way of proving your log state very efficiently. So I send out a checkpoint message. If I get 2 F+1 digests that match, I know that I have a quorum of honest nodes who agree that we can form a checkpoint at that point in time. So we form the checkpoint, and we can throw away the log entries before that. So now we can truncate our log.
Why isn't it just F+1?
Because I have to do it in finite time. And I'm not guaranteed that I'll ever get a consensus in finite time with F+1. And so everything that we do has to be a quorum except for the client. Because the client isn't part of our consensus. So if I had F+1, right, I wouldn't know that I was partition safe. Right? I don't know that there isn't another partition who's decided to checkpoint at a different point in time. But I have to have a quorum, and the 2F+1 gives me a quorum that guarantees that I'm partition safe. So that always comes up, right? This partition safety is, and if you look at some of the other protocols like Stellar, the Stellar protocol is all about quorum management because it tries to fudge things in a different way. So view changes. View change means I have a faulty primary, or I have enough faulty nodes that the client never gets F+1 replies. Somewhere the 3-phase commit failed and never got back to the client. Because the primary is deterministic, right? I can change the view. Changing the view changes the client. So each primary, has its own view number. And if that primary is bad, then that whole view could be bad. So your comment about I've got to roll it back, this is where the rollback happens. So I want to restart a view by reissuing pre-preparers from the failed view, but in a new view, so that I can make all of those operations happen. So how do I trigger a view change? Well, the client can trigger it. The way client triggers it is that it rebroadcasts its request. If a replica gets a rebroadcast request, it starts a timer. And when that timer expires, it sends a view change request. If a replica doesn't see the commits come back, it can start a timer and say, hey, I didn't get enough commits, so I can't commit this. I don't want to just have it sit here forever. So once the timer expires, I'm going to request a view change. So anytime you don't have liveness, because things didn't go all the way through to a reply, you're going to have a timer expire. And so this is where the weak synchrony comes in, and then you're going to say, we need a new primary. And so if there are 2F+1, where the one includes yourself, view change requests, then I now have a quorum that have agreed to change views, and I'm going to change views. So view change is a big message, because I have the faulty view number, which is B. I have the sequence number of the last stable checkpoint S, and N sub S. I have a set C of the 2F+1 checkpoint messages. So that I know that I'm talking about the same S. Now, if I had a Merkle tree or some other way of guaranteeing that because they don't use Merkle trees in PBFT, that I might not have to send the whole set, right? But in PBFT, they send the whole set. So I'm sending all of the checkpoint messages. So if If I have 16, I'm sending a set of, 16 minus F, 12 messages or something like that. P is the set of sets. So this is where it gets really verbose. P sub M is the set of all the pre-prepares and prepares after my last stable checkpoint N. So I'm basically going to send, this is my state. I'm a replica. Things stopped happening at N. These are all of the messages, all of the prepares and pre-prepares that are currently in my processing queue. So I might have 12, three-phase commits queued up that I'm in the middle of trying to complete, and one of them stopped, and so I want to change the view, so I have to send all of those. And all of those view change messages have to match. I have to have a quorum of them. Well, as long as I have enough honest nodes, they will match.
What do the nodes do with all the pre-prepared and prepare messages?
Well, that's so that the new primary knows which ones need to be restarted. So even though I had 15 messages that were in various stage of processing under the old primary, and that old primary was faulty, was Byzantine, was lying, where he just died, he just went offline, and they didn't complete. So now I have to get a new primary, and I don't want to throw them away. I want to start over.
And the new primary couldn't just use its message log and what it's received.
Well, it needs to know that it has a quorum of people that agree that it should be a view change, and the view change should restart all of these views. Because if they're not in agreement, then I could have the new primary, be malicious, right? And so at every stage, I have to have a quorum that guarantees, my liveness and partition safety. And that's why every time I do anything, it has to be 2F+1. Because if you back it out and say, well, if I don't have 2F+1, then you can figure out a way for the system to fail. Because you don't have a quorum of honest nodes guaranteeing that whatever you do, everybody's in agreement on. And that's the core idea.
So it's really a way of fast forwarding to here's the current state.
Yeah.
Instead of doing lots of.
Well, the thing is, I don't want to have to talk back to the client because the client wants to put stuff out there and guarantee that eventually it works. And so the goal is I've got all of these messages that are in some stage of processing. They've all been ordered, and I want to write them to the log in that order. So the pre-prepares, because they each have an N and a view, they're all ordered. And so I have to restart them, and I want to restart them in the same order. Right. And so somebody can lie about the order. They can say, well, this message was at this end, not this end. Well, as long as I have 2F+1, they can't. I know that I know the right order. It didn't get lost in the process.
So you've got to have all your committed but not yet checkpointed.
That's right. So that's what I say. It's from the last checkpoint.
I don't know that that's true. I think that it's the case that if the client hears back that something has been committed,
they will alter
they can,
the current state.
Yeah,
I think it's the case that anything that's gotten through to the point where the client, like if 2F+1 got to the commit
you don't know
phase,
but you don't know that the client actually got this F+1.
No, I'm not saying that the client got the F+1, but if we get to the point where 2F+1 got to the commit stage, I think that it's the case that there isn't an expected rollback from that scenario. It's anything prior to that could get rolled back.
You could be right, but
It seems like
the definition in the paper says from the last checkpoint. That's the way it's written.
it seems like that would be challenging to write a client against that API, right? In the sense that
The client doesn't.
the client has to wait for a checkpoint, which is
No, the client doesn't have to wait for a checkpoint.
Well, the client
view
can't-
stage among the replicas, not.
This is just to make sure that the new primary finishes all the processing. So it's maybe the commit state, the client's good, he can go away. But
okay, that's right. Yes, that's all I was saying.
yeah, the client can go away, but you still have to make sure that in the current view, you commit everything and get to a stable checkpoint so that you can throw it away.
Okay.
And since you haven't got to a stable checkpoint, you've got to make sure you rewrite it and get a stable checkpoint. And anytime you have a view change, anything that was from the last stable checkpoint could disappear because the new primary could also be Byzantine, fault. And so
Yeah, you've got
you
to
have
match
to
everybody's state from the last checkpoint, and everybody has to agree on that.
Right,
when you're
everyone
getting
has
the
to,
new view.
right, but it is, I think it's the case that once the client receives if the client receives F+1
the client's good.
results, the client doesn't have the expectation that that operation will change.
That's
Like the behavior of the perceived linearizable system
That's right.
will look consistent externally.
Externally, yes,
yes.
but only because the view change
Right.
guarantees
Right.
that even though the client has gone away, it's going to fill in
It's
the
going-
blanks.
right.
And make sure that the next
They all get
checkpoint,
applied in the same order.
they all get applied in the same order.
Okay.
Even though the client is done, it might
Right.
take some time before it gets written. So once the new primary receives 2F+1 matching, where the one is its own, view change request, it then sends out a new view. You broadcast a new view, he then puts all the view change messages, he has the set of pre-prepare messages, so now everybody knows, okay, we're gonna start over with all of these pre-prepares, and they all have an end, so they're all gonna be in the same sequence, but now in a new view. And so he basically just batches a whole new set of pre-prepares and pre-phase commits. And if he's an honest primary, they're all gonna complete and get written. And so every so often, you're gonna hit a dishonest primary, and then you go through this huge cost. And if I had 4 or 5 dishonest primaries in a row, I just keep doing that, until I finally hit an honest primary. And then it finally get written to the law. So, if the power went out during that time frame, you're covered, right? So PBFT is practical because under normal operation, where I don't have Byzantine faults, it only costs me about 10 to 20% over something like Raft or Paxos or some 2F+1 algorithm that is just doing log replication without Byzantine faults. And before PBFT, you were 2 or 3 times at least slower, not 10% slower. So that's why it's practical. But if I have view changes, then my performance could degrade as much as 90%. And so it's not robust in terms of having stable performance when I have Byzantine faults. So I'm tolerant to Byzantine faults, but I'm dependent on those faults being rare for me to have any kind of reasonable throughput. If those faults are not rare, then my system drops to its knees. And so it's impractical in that sense. So there's several papers where people say the practicality of practical Byzantine fault tolerance that they're talking about is performance under fault. So there are quite a few implementations. I've got some of them up here. Tendermint, these are open source implementations. That's a cryptocurrency transaction settlement based blockchain for transactions. Aardvark is an attempt to improve the robustness under failure. It did pretty good, but it's not the end of the world. Fast Byzantine consensus is what I talked about, where they have 5F+1 and they have a 2-phase commit. And so both Ripple and Stellar are based on fast Byzantine fault tolerance. And what they do is they separate the consensus ordering of the primary from the validation. They have two different sets of nodes. So they can do a 2-phase commit, have a different set of nodes that's validating. So essentially, you can do it faster, but you have to have many more nodes. And we don't have time to go through that. BigQDB is an example of PBFT managing a Rethink DB database. So you basically, the rights to your database are governed by a distributed consensus pool. So now you can have, people that you don't like or don't control all collaborating to write the database. You guarantee that unless, you have a majority failure that you're getting good stuff. Hyperledger is the Linux Foundation, and it's under the hood, it's a PBFT. And it was originally written in Erlang. For some reason, they decided to rewrite it in Java, which is surprising. If you know my background, Python fanboy, I have never have good things to say about Java. So the state of the art right now for fixing PBFT, we don't have time to go through this in detail, is redundant BFT or RBFT. And so there are a couple of papers that you want to read. One is the redundant paper, and I have the link up there. The other one is a paper that won best paper at distributed consent at an annual conference where most of the work on distributed consensus is published. It won best paper, and it's called the next 700 BFT protocols. And what the paper does is it breaks BFT into components. It basically says, here's the components, here's the execution blocks, and by mixing and matching these, you can come up with any kind of BFT protocol you want. And you can trade off, CF+1 versus speed versus redundancy versus those things just by mixing and matching these. And one of the things that you do is that you run multiple versions of the protocol concurrently so that you can switch between them. And so this allows you to improve performance. So redundant BFT actually is that. So if you look up here, this is for the minimum F equals 1, right? So F equals 1, I have 2, on each node I'm running 2 different BFT protocol instances. So I'm running so that's why it's called redundant. I have 2 complete sets of BFT nodes running on each node. And for each set, there's a different primary. Since at most I can have 1 failed primary, because F equals 1, I only need 2, right? So if F equals 2, then I would need to have F+1. I need to have 3 redundant instances running, right? But it's only F+1. It's not 2F+1, right? So
It's a lot of messages.
It's
a lot of messages.
But it's not, because if you think
If
about
you
it,
pack them together.
you can pack them together, you can batch them, and if you think about it, BFT protocols are network bound, not performance bound. So if I got a multi-core machine, essentially running other instances of the protocol is free, right? Unless I'm, from a performance standpoint, not a cost standpoint, but from a performance standpoint.
The signatures would be different.
The signatures would be different, right? No, the signatures can be the same.
The view number will always be the same.
No. Yeah. The keys for the signatures are the same.
Right. Yeah.
The actual signatures are different because you're signing different packets.
Right.
But the key management is not any more complicated.
I'm just saying as far as CPU overhead goes.
That's right. Yes. You still have that CPU overhead. Yeah. So what happens is that in redundant BFT, I add an additional step, a propagate step. So what happens is that the client sends the request, and I then propagate the request by broadcasting, every node broadcasting to every other node. And that guarantees that every protocol instance gets the client request.
The poor network.
Huh?
That poor network.
Yeah.
It's too bad it's not called pre-prepared.
Yeah, that would have been, that would have been nice.
And then commit could be paired.
Right.
Post-paired.
So now every protocol's instance, the primary and every protocol instance, the replicas in every protocol instance are guaranteed to get 2F+1, instances of the request. So they know that they're all starting with the same set. They're all guaranteed to get the same set of requests. So every protocol instance has the same set of requests from all the clients. That's why you need that additional step. And I have to get the 2F+1 to get that. Now, each of them just runs their 3-phase commit and sends it back to the client. Now, if they're not the active protocol instance, they don't reply to the client. If they need a view change, they just say, I want a view change. But guess what? They don't have to do the view change with all of the state and everything because the backup protocol already has the correct state. Because they have the same set of pre-prepares, they have the same sequence ordering, it's all going through it. So basically, it instantly switches to a backup and completes. So there's no performance degradation, it's like 3%. So basically, you have consistent performance all the way through, even in the presence of Byzantine fault, at the cost of having
The propagate step.
the propagate step.
That trick feels like one of those things, it's like, solve Byzantine failure, but this one weird trick.
Well, but understand, the point is that now that I've solved it, I can dependably build infrastructure outside the firewall, outside of a cloud, outside of my private cloud. I can build it in the fog, and I know that I will come to consensus reliably and dependably with consistent performance. Now, that performance costs me, but it's consistent. So I can architect, I can build on top of that.
Choosing F is hard.
Yes, choosing F is hard.
That is actually my question.
Okay, so choosing F is really based on your failure surface, your attack surface, right? Survivability has, there are three aspects to survivability from the military perspective. One is called susceptibility. Susceptibility is how big of a target are you? Why would someone want to attack you? How visible are you? So if I'm a big infrastructure and I have millions of credit cards, I have huge susceptibility because people want to attack me, right? They know about me, they know where I am, I'm a target. They're gonna lob bombs in my direction. Vulnerability is, once attacked, how likely is it that I will fail in the attack? So if I'm a big target, vulnerability says I gotta have 3-foot concrete walls so when the bombs land on me, they don't get through, right? And then the final phase is recoverability. That is, once you have a failure, can you recover from it? How long does it take you to get back in operation? And for many critical computing infrastructures, recoverability is a problem because what you're trying to prevent is leaking of information. And once the information leaks, you can't ever get it back. So you have to be really good on the vulnerability part. And that's why Byzantine fault tolerance is so important. Because if you have a fault tolerant system, it doesn't matter how many bombs they lob at you, they can't take you out. As long as they don't have the resources to lob bombs at every one of your nodes simultaneously and overcome them with an exploit. And so you have to decide what your opponent looks like and how many resources they have and how hard they're going to try to overcome you to decide what F needs to be. Because you can calculate a probability.
The scenarios that you described not only accounts for some possible way. Consider, you obviously, you guys know more about space than I do because you work with it. But when you guys are dealing with that, you also have to deal with faults that occur because you can't rely on the networks of all the different nodes. You've got different quality of networks there, right? So even if you're not doing something like that, you have a different quality of servers in the fog you can't rely on, and you can't know when.
But you can tune for that based on your timeouts. So if I know that my network's going to be out at most an hour a day, I can set my timeouts to be greater than that. And so I will still come to a consensus within a bounded time despite my network being out.
Okay, but what if you're using this in your own infrastructure? How do you account for things like want to be able to do planned maintenance on a single node in the system without having to bring the entire system.
Right.
So you've got-
Very good question.
nodes that you're going to bring down intentionally also, right?
So that is part of the permissioning process. Because what we haven't covered is how do I prune bad nodes and add in replacement nodes?
That's usually the second half of every distributed
That's
protocol
right.
paper. Is like
So,
the whole
so
second
that,
half of
that's,
the paper is
that
here's
is,
how you
that
make
is at
your
least
change.
another 2-hour-long lecture. So most of these systems have something in place. That's one of the reasons that Bitcoin algorithm is such a nice algorithm, because it already solves that problem. Because I don't have to permission the nodes. I can have thousands of nodes all come in whenever they want and it still works. It's just really, really slow.
So in the case of where you choose F poorly, do you know that you chose F poorly, or is there any?
No, you don't.
Oh, so this is like the, so there even isn't necessarily like, oh, we had one more that got
You don't know.
turned over, okay.
You have no way of
Is
knowing.
there any variation, or you, I mean, I guess not.
So for example, in Ripple and Stellar,
So you know the class, right?
yeah, in Ripple and Stellar, their approach is to use a probability. So you have these speculative approaches to DFT. So Zika, I can't know if I pronounced it right, the example, but Ripple and Stellar, what they do is they say, you want to compute the probability of the nodes colluding to defraud. And then you can pick the F based on that probability. And so it's a probabilistic guarantee, not an absolute guarantee. And so you can back out the F from that probability. So if you're good at computing the probability and you believe your probabilities, then you come up with a reasonable F. And Ripple didn't do it right. Huh? So Stellar didn't do it right. So Stellar originally was a copy of Ripple. They just took the Ripple protocol and said, we want to do our own stuff. We don't like the way Ripple does stuff. And they got the probabilities wrong, and so they had a failure of their blockchain. They had a partition and they failed. And so then what they did is they spent a bunch of money and got some smart people to come in and fix it. And now Stellar has a protocol that is now the Stellar protocol that is not a ripoff of the Ripple protocol. And it's a very nice protocol because they have some very good proofs about core management so that they can pick the F much better. So, yes. No, I'm just saying, so that is an active, that is probably the area where there's the least amount of surety and the most amount of variation is managing your consensus pool. How do I bring nodes in? How do I prune them? How do I do things like take a node down? So for example, if I say F is 10 and I have 41, I got a problem. But if I have 100, I've got plenty of extra honest nodes, right? So I can at any point in time say, hey, on this next view change, we're going to have 99 nodes instead of 100. Who cares?
So one other question I have that has to do with the client. So in the algorithm as you described it, the client also has to know what the F is that all the servers
That's right.
are assuming, right? So does that mean that you can't have a system where the
Nodes join and leave.
well, no, where the client doesn't have intimate knowledge about the F that was chosen for the servers? Or is there a way for
Yeah, you could.
a client to just come and say,
Yeah.
"Hey,
So
why
so
can't
one
you
so
use
one of the ways you do that is that you actually have a site where you publish the interface for your consensus pool. And so the client will go to that site and it'll tell them what the F is itself. It'll tell them what the key, what the public keys are for the consensus pool, and so he can bootstrap just from without having to know any more than that. Like,
You've got to have some way to reliable information about the nodes you require.
and that's a permissioning process, right? Right. So that's why it's called permission blockchain, because there is this layer of stuff that you manage, but that once you bootstrap to that point, you don't have to worry about it not coming to consensus. So something that might be helpful to you is that I worked as an architect for Evernym, and part of that work is we developed something called the Plenum RBFT implementation. So it's a Python implementation, so it's pure Python, so it's easy to walk through. And it's Apache 2. It's an RBFT implementation. It also uses RAID, which is the Reliable Asynchronous Event Transport protocol that I wrote, which is a UDP-based protocol that uses libsodium. So it's a fully end-to-end encrypted, signed, really fast UDP protocol. And so that's up and running, and you can, there's actually here, let me, like, if you go here, oops, why did that do that? Why did that? Oh, I can't do that on this slide. Here, I want to exit. This one. So if you go here, you can go to the wiki, and there's quite a bit of. Huh? Oh. Yeah. Sorry. I'm in the two different. I'm not in mirroring mode.
On your comment about latency, one of the interesting things I think about these sorts of systems is, so there's 3 F+1 nodes. You only need F+1 responses,
Right.
which means that 2 F+1 need to have successfully agreed, which means that you only need the F+1 fastest honest nodes. So from a latency perspective, even if there's a high degree of variability, you're sort of choosing from the fastest tail of that distribution. Because you don't, you can, the long tail you can just cut off. Like, you're only waiting for the first F+1 to respond. So that really does help a lot with the perceived performance.
Slow busy.
Yeah, so there's actually quite a bit of, good information here. There's a nice command line interface where you can stand up nodes, just run them and run through an election. So it's a pretty good didactic way that you can get familiar with redundant Byzantine fault tolerance. So I think that's a reasonable thing to.
That's super neat.
And I've said this before, but if you're trying to build infrastructure outside the cloud, you really want to do everything end-to-end encrypted and signed. You want to use best practices, and SSL and SSH both aren't end-to-end encrypted with signing after encryption. They're signing and encryption. They're done in parallel, so there are many more exploits. If you sign after you encrypt, there are very few exploits. And so all those protocols were developed when people thought that performance was so important that they're willing to fudge on security. And nowadays, you just don't fudge on security. Always sign after encrypt. So here's something that might be interesting, which is, how do I scale Byzantine fault tolerant out to lots of nodes? Because if you think about it, it doesn't scale very well, right? I mean, if I've got 16 nodes and I'm broadcasting 15 messages at every step.
Especially if you've got like
the redundant
one, and you're trying to do it over Wi-Fi.
Yes. Right. So if I happen to be doing something where I'm using a ledger, then I can do something called mesh anchoring. Right. So if you think about the checkpointing, where I'm doing checkpoints, if I have transactions and I register transactions between consensus pools, then I can leverage the fact that each consensus pool is anchored with another consensus pool, so that if somebody defeats one of the consensus pools, they can't unravel it past the last anchor to another consensus pool unless they also defeat that other consensus pool. So now I can build the equivalent of a 1,000 node consensus pool in terms of my security without having to have 1,000 nodes in my consensus pool. So that's one way to scale. Another is to use like a distributed hash table so that I can load balance all my client requests to different consensus pools. And then I can keep my consensus pool small. And so, 16 is a pretty hard number to break, right? And that's not an unreasonably sized consensus pool. And so now I can geographically distribute them so that they're close together, and so now I can build in the fog. I can build pools that are neighborhood pools, so they're all close together, so the latencies are small, but I can still distribute it across a lot, thousands of nodes. And then here's an example of repetition identity. I won't go to that in detail. So there you go. Any questions? Yes.
So I think with Ripple and Gold Stellar that they use sort of like centralized authority for the permissioning
Yes.
mechanism.
Yes.
What is there any sort of? It seems pretty a natural extension that say, okay, we have Bitcoin, which is pretty good at just letting any old node join the network. Where we can sort of imagine a system where, hey, the cost in terms of joining this pool is some, we determine that cost based on the probability of that we think like as our network grows inside here, that you could then like attach something in front of Bitcoin to sort of proof, say like, oh, are you going to be a valid node on the network? Kind of see if they're willing to pay that cost in terms of proof of work. Does that kind of make sense?
Yeah.
Has anybody like played with that? Because that seems like a pretty natural extension to sort of combine those two ideas.
Yeah, so Tendermint does that. They use a proof of stake to manage who gets to be in the pool, which is some cost, some investment that you make.
Assuming that's enough to incentivize you.
Incentivize you. Factum uses, now Factum itself is a proof of stake system, but they use a governance policy that could be used with a Byzantine agreement. The way that works is that they have a set of nodes that are the active nodes, and then they have a set of candidate nodes that run as part of the consensus pool. And what happens is that the nodes of the actual nodes monitor the performance of the candidate nodes. And when a node fails, they kick out the node and bring in the top candidate automatically. And so basically, if you want to be in the thing, you have to be a good citizen for a long period of time and be fast and have low latency and all those things so that you get to be the top and get loaded in. And so you have an automated way of governing who's in it. And actually in RBFT, because I have these backup protocol instances, one of the things that deciding which backup to go to is no longer deterministic. It's no longer the view determines which one. It's actually based on some sort of performance guarantee. So the backup protocol instance that I pick is the best performing one in terms of latency and things like that. And so I could actually have the way I bootstrap nodes into that protocol is to actually bring in backup instances and let them run in backup mode. And when they prove themselves, the next time I switch to the backup ones.
Do the nodes know when they're being brought in?
Yeah, because they win the vote.
Because they could start being malicious at that point.
That's right, they could.
If you're heavily funded enough, you could create some really high-performance sleeper
That's right.
bad actors.
That's right. So
Change the probability, right? Like
Yeah.
just tuning in, right?
it's the probability, But the thing is that with all of these things, when you do that, it's like it's a one-shot deal. As soon as you're dishonest one time, that's it. You're done. You're gone. You were dishonest. That means you're dishonest forever. You throw them out, and you've now exposed yourself. It's like you're a double agent, and as soon as you are burned, you're burned, right? So in a lot of cases, limiting the value of any single exploit means that there's no incentive to be dishonest.
So I guess I'm wondering how, going back kind of to Addison's question, how do you detect that a node is lying?
If they vote and they don't
But
agree with
how
the
does that
quorum-
look different than, okay, so the clients would have to figure it out?
No,
Because-
the other
because
replicas.
If
because-
the other replicas have a reporting system, then a malicious node could report good nodes.
That's right, but because every node reports its votes to every other node,
Okay.
and the honest nodes always know who the
So
dishonest
then
nodes are.
there's some central reporting thing that's getting
Yeah.
updates from everyone,
Yeah.
and they can figure out.
And they can figure it out. As long as any
Non-
decision you make at any stage is always 2F plus 1, then you're always guaranteed
Yeah,
that
okay.
it's a good decision. It's a correct call.
But how do you tell the difference between a malicious node and a trustworthy node that had a bug corruption on the network when they were reporting back?
So you want to, right?
Well, corruption on the network, you're signing messages. So corruption on the network looks just like they're delayed. The message never got through. And that's why we have the 3F plus 1. So I can have F, honest nodes that never respond, and that accounts for all the network errors.
So the only, do you treat them the same as you do a malicious node? You said
No, because they don't respond. They didn't lie, they just never responded. There's a difference.
So that's part of the timeout.
The timeout, it just says they timed out.
That's okay, timeout.
See, there's a difference between an error, which means the signature doesn't validate, and a validated message that doesn't agree. That's a lie. Right? So if I send a validated message that doesn't agree, I lied. If I send a message that doesn't validate the signature, then it could be a network error, and that just means it didn't happen.
Yeah, so more pernicious would be disk errors.
Yes.
Could cause a bad response, or a bug.
A bug. Yeah.
But I mean, you would still want, because that could be like a form of attack, right? Whereas for a whole bunch of nodes that are, hey, we're just never gonna respond, and that, slows down the network to enough where, oh, it's now more likely that you're susceptible to some other attack, right? Like that is.
Yeah, but that's why the 3F plus
Right.
1, because you're saying that at least,
You're capturing at least that many. I guess the point being is you would still sort of want to eventually call nodes that are always being timed,
Yes.
always.
and that's what
Always
redundant
erroring.
BFT does, is essentially any nodes that are slow never get to be the primary. You just have enough backup instances, and so a slow node never gets to be the primary because its backup entrance, when it is primary, while it's running a backup, right? Every node that has a primary is always running, so all the other nodes can collect statistics on it all the time. And if it's slow, it'll never get elected to be primary. So it'll never slow the network down. Unless it was malicious, right? And then it would be fast until you got elected, and then it slowed down. But as soon as it slowed it down, then you would pick somebody else, switch over, and then you go, hey, you lied to us about your performance. We're not going to ever pick you again.
So can you get non-malicious, incorrect information, not so much a lie as, a client send a message to him and I guess you just wouldn't be able to fully commit anything in that case. So.
Well, if the client sends you a message that isn't one of the valid operations, you'll throw it out.
Well, no, I mean, he sends you a valid message and maybe you've got something that looks like consensus, but it's not. But no, that's what your 3F.
That's what the 3F, yeah. That's why you have to have the 3F plus
Right.
1. And so, yeah, it is one of those things where you think about it, and that's one of the reasons why almost everybody that does BFT algorithms does some derivation of PBFT, because a lot of people have thought about PBFT, have thought through the proofs, and they've all decided that it works. And so anytime somebody comes out with a different algorithm that tries to do it in a different way and doesn't have these, partition safe proofs in it, then people are suspect because it goes, well, have you thought about this? Have you thought about that? And so it takes a while for somebody to accept the protocol as a valid one.
Same kind of true with Paxos before RAF came out. Before
That's
RAF
right.
came out, everyone was like, no, you just do Paxos.
Just do Paxos.
Just do Paxos because Paxos has proofs.
The funny
Yeah.
thing is that this is based, well, at least it looks like it has Barbara Liskov.
Yeah, no, this is very
use-stamp
similar to,
replication.
this is very similar to, yeah, use-stamp.
Use-stamp
yeah.
replication
Also,
Yeah. Well,
came
the
out at
two-
the same time.
this Paxos, it seemed like it got way less traction for who knows
Yeah.
why.
Yeah.
Yeah,
So,
and
so the
I've
2F+1 is there for,
Yeah.
yeah, but to get Byzantine, you gotta go 3F+1, and that's the difference. And an additional stage, instead of Paxos is 2-stage, you get PBFT 3-stage, you have an additional F, you know. But it all starts to look the same after a while. Everything looks like Paxos somewhere.
Yeah. It's all built out of the same building blocks.
Yeah.
Yeah, I thought the next 700. Yeah, it's a reference to the Peter Landon paper, the next 7 programming languages.
Oh, I didn't know that.
Yeah, it's now a talk name or a paper name. They're
Kind of like considered harmful.
Yeah.
Paper names.
Yeah.
Yeah, paper names program which is considered harmful, yeah.
Yeah, the next 700 programming languages is by Peter Landon, late 60s, early 70s or something about. It's basically the foundation that all modern functional programming languages are built on.
I'll have to look for that.
Yeah, it's a very interesting paper. Has nothing to do with distributed systems.
All right, thanks. Okay, so sort of bookkeeping stuff. Thanks for coming. Please take the food out so that I don't have to. So please take some leftovers. As far as what happens for next month, given our schedule, we've been doing like practical stuff, then sort of more paper. So this was a paper month. So next week would be a practical month. I don't have a topic or a speaker lined up. So I think what I'm going to do is, if anyone's interested in or knows a particular topic, like you don't even have to be the person to give the talk, but if you have sort of a practical topic you'd like to see covered, let me know by I don't know, 2 weeks, 3 weeks from now, 2 weeks from now, and then I'll try and get that lined up. If we end up still not having a topic and I can't think of one, then we'll just follow up in June. So I'll definitely have an idea by then. So yeah, so just let me know if there's something you'd like to cover, but otherwise we'll continue with the paper in June. I have sort of a big list of papers that are really interesting. So okay, yeah, thanks for coming. Take some food on the way out. I think the doors locked at 8, so if you need to help getting through the building, I've got a badge and I'll help you through. So thanks again.